Welcome to this lesson. This lesson taken from paper 2, physics 11, that is principle P510/2, paper 2. The section A, that is light, and therefore I'm going to start from defects in lenses. Defects in lenses. Okay? So you can say defects in images, actually, in images or aberration. Defects in images or aberration. So when we talk of defects here, this occurs, okay, this occurs due to distortion of images in lenses or curved mirrors of large aperture. Of large what? Large aperture. Then we shall say that when mirrors or lenses are, now there are two types of aberration. There are two types of aberration. Aberration is double R. One, we have what we call chromatic aberration. Then we have spherical what? Aberration. Spherical what? Aberration. So we shall now start with chromatic aberration. Chromatic aberration. Then when we say chromatic aberration, of course we are saying that in lenses or mirrors, you find that the images are distorted, or the images are blurred, or the images are not clear, or there is overlapping of images. So that defect in images is what we call aberration, or is what we call defects in images. And that one occurs as a result of image being distorted in both mirrors and lenses of wider aperture. Okay, so we have two types: chromatic aberration and spherical aberration. So when we start with the chromatic aberration, we shall say that this occurs only in lenses. That's the first point to note. Occurs only in lenses. Then we shall have. Let's have this one. That's a lens. Then we shall have white light. This is white, right? So we shall have this, and we shall have the other one. Okay? So you know white light is what? White light is dispersed, okay, or is splitted by the lens, producing, let me say, the red and blue. So this is red, this is blue. So this is a focal length for red. This is a focal length. This is focus for what? For blue. Okay. So we shall now say when white light is incident. When white light is incident on a lens, what happens is, tell us the different colors components. Different color components are refracted differently. Of course, the one which is mostly refracted is red. The least refracted is what? Is it blue? Then we say, are refracted differently. Then we shall now say that images corresponding to different colors are formed. Images corresponding to different colors are formed at different points. At different points along with the principal axis. Principal axis. Okay? Along with the principal axis. Then image viewed has curved edges. This leads to overlapping of images with colored edges. With colored what? Colored edges. This is chromatic aberration. So we are saying that when a white light is incident, different colors are refracted differently by different amounts. Therefore, different colors are brought to different points along the principal axis, resulting into the formation of broad overlapping colors along the principal axis. So this overlapping is what we call the chromatic aberration. Then we can now go ahead and say minimizing. How it is minimized? Minimizing chromatic aberration. Chromatic aberration. How do we minimize this one? We can say it is reduced by using chromatic doublet. Is that a spelling? Minimize it by using chromatic what? Doublet. Chromatic doublet, like that. Chromatic what? Doublet. It consists of convex lens and concave lens of different materials. Of different what? Different materials. Okay? Of different what? Materials. Then we shall say, okay, that the convex lens deviates the rays. The convex lens does what? Deviates the rays. Deviates what? The rays. Okay? While concave lens nullifies the division. While the concave lens nullifies the deviation. Yeah? The deviation. So we shall have like this. That's chromatic doublet. Such that this is a concave what? This is convex what? They are made from different what? Different materials. Okay? Then we shall also say, properties for lenses to be used. Properties for lenses to be used in chromatic what? In chromatic doublet. What are the properties? Of course, we said there must be two lenses of different materials. So the first one should be lenses should have different materials. Lenses should be made be from different what? Materials. Flint and coal. Flint and what? Coal. Those are two materials that these lenses should be made from. Then another one. Another one we can now say the ratio of their focal length should be equal to the ratio of their focal length should be equal to the ratio of their dispersive powers should be equal to the ratio of their dispersive powers. Dispersive powers. You know, power is equal to 1 over F, okay? 1 over F. So when you get the two powers and you divide them, you realize that you get the ratio of power and the ratio of their focal length. So the ratio of their focal length should be equal to the ratio of their dispersive powers. Then next we shall say that the separation between them should be equal to the mean of their focal length. The separation between them should be equal to mean of their focal length. Cool. That's if they are not in contact, okay? That's if they are not in what? If they are not in contact. Then we say if lenses of the same glass, if they are lenses of the same glass, then they should not be in contact. If they are lenses of the same glass, of the same what? Glass, then they should not be in contact. They should not be in contact. So that one is done. That's chromatic aberration. Then we go to spherical aberration. And next we go to spherical what? Spherical aberration. Spherical what? Aberration. Spherical aberration. So we shall now say that spherical, this is a distortion of the image by either lens or mirror. This is the distortion of the image by a lens or a mirror of wider aperture. Of wider aperture. Then we shall now say occurs both in lenses or mirrors of wider aperture. So what happens if it is the lenses? The mean is that you realize that we shall have marginal rays and paraxial rays. So those rays which are far away from the principal axis, after being refracted, when they converge at the principal focus somewhere, they will converge at some point whereby that the paraxial rays, those which are close to the principal axis, will instead converge far away from the point where the marginal rays converged. So meaning that if you have very many parallel beam of light, many rays, then you are going to have images formed on different places along the principal axis, resulting into broad images. Okay? So we shall now say here, for the lens, for the case of the lens, let us use the lens. Say this lens. Okay? So we have these ones. Paraxial rays converging very far. This F is here. We can put some image 1. Then we have marginal rays. Marginal rays, they converge here. They converge here. Marginal rays. So that means that this one can call it maybe F1 for these rays, and this one can call it F2 for. So what do we explain here? We go ahead and explain how that one occurs. Okay? How the marginal rays are refracted to different points, and then paraxial rays refracted to different point. So we shall say when a wide beam of white light, okay, we can say when a wide beam of that's one, right? A wide beam of light is incident on a lens, the marginal rays, those which are far from the principal axis, the marginal rays are brought to a point closer near the lens, while paraxial rays converge at a point far from the lens. This results into formation of broad image, okay? Broad image. For the case of in spherical mirrors, in curved mirrors, we shall have something like this. Then let me put it here like this. Trap this in curved mirrors, principal axis. So we have paraxial rays and marginal rays. Paraxial rays and marginal. This is paraxial, this is marginal. So they converge far away. Like this. Okay, they converge here. Then this one, you see, the marginal rays converge here, resulting into formation of broad image due to a series of multiple images along this principal axis. So how do we minimize this? Minimizing spherical aberration. Minimizing spherical aberration. Minimizing spherical aberration. So how do we minimize? Okay, in lenses In lenses, it is done by using an opaque disc which cuts off marginal rays, marginal rays, okay? Which cuts off marginal rays. An opaque disc with a hole at the center. Opaque disc with a hole at the center, so that marginal rays are cut off, and only central rays are allowed to pass through. That's one. Then in mirrors, in what? In mirrors. How do we minimize this one in mirrors? In mirrors, it is minimizing by using parabolic mirrors. Parabolic, it is minimized by using parabolic mirrors. Okay, it is minimized by using parabolic mirrors. Okay, because the parabolic mirrors converge wide parallel beam of light to a single focus. Focus. Yeah. Now, what is the comparison of a narrow and wide aperture lenses? Lenses of narrow aperture are widely used in optical instruments so as to avoid spherical aberration. This is because when a wide beam of light falls on a lens of narrow aperture, central or paraxial rays are brought to the same focus to form a sharp image. However, with a wide aperture, it allows both marginal and central rays, which thus are brought to different points along the principal axis, hence formation of broad image. Okay, so that's what we have. Then we can move on and we also start another section, another subtopic. This is called optical instruments. Okay, so our devices are which aid or help eye in what? In viewing. These devices can be like telescope, can be microscope, okay, can be spectacles. Yeah. Then we shall now say terms used. We shall look at the eye as optical instrument. So we can look at terms used. Now, under the terms used, we shall start with the near point. And then we shall define the near point and the nearest point at which the eye. Nearest point at which the eye sees or views the object in details or clearly. So there's that point from your eye where you press an object and you are able to see it in details. You are able to see it clearly. That point is called near point. The distance is called what? The distance is called the distance of distinct vision. Distinct what? Visual. Which is d approximately equal to what? 5 centimeters. So we shall say that it is what? We shall say is the shortest distance of the eye from the object. Is the shortest distance from the eye to the object, from the eye to the or image, by the way, from the eye to the object or image in which or image in which the eye can see it clearly, can see it in details. So the distance is about 25 from your eye. Okay, when you put an object at 25 here, you are able to see the object clearly or in its details. That distance is called the distance of distinctive vision. That point is called what? Near point. The point at which the object is placed so that it can be seen in its details. That's it. Then we go to visual what? Visual angle. Next is visual what? Visual angle. Now in visual angle, we shall say that is the angle subtended by the object, or image at the eye. At the what? At the eye. So that's what we call visual angle. Then let us go and look at let's look at something like this. Let us look at this one. So we have this is the eye lens. Let's wait here. This is the eye lens. And then this is the eye. Okay, it is seen, yes. Then you can put here this axis. Then you put an object here. This is object here. Then forming an image somewhere here. Forming an image here. Let's say the distance here is A. The height of the image is B. The angle subtended is theta. Also, this angle is what? Theta. So we shall say for small angles in radians. For small what? For smaller angles in radians. Okay? We shall now say tan of theta is approximately equal to theta, which is opposite, that's B over A. So this implies that our B will become A theta. Then we shall say, since A is fixed, then it means B is proportional to theta. What does that mean? B proportional to theta, meaning what? Theta is the angle subtended at the eye. I see that angle subtended at the eye. So I shall say to implies that the angle or the size of image or object depends on the visual angle, subtended at where? At the eye. At the eye. Okay? So what does that mean? It means that it implies i.e. the bigger the visual angle, the bigger the object, the bigger the size of the object or image. Then we shall go ahead and say this explains why. Okay? This explains why Why the further vertical pole? This explains why a further vertical pole. A further vertical pole in line with others of equal heights. In line with others of same height appears shorter. So what does it mean? If this is the eye, okay, and then you have, let me say, of the same height. So this is pole 1, this is pole 1, this is pole 2. So we shall have this, then we shall also have this, like that. So the angle subtended is theta, the angle subtended is alpha. Then here we shall say this is image of 2, then this is image of 1. So what I'm going to say? What do we say here? We shall say that the image size depends on the visual angle. Okay? The image size depends on the visual angle. So we shall say first the image size depends on the visual angle. Let me say, since pole 2 subtends a small visual angle, a small what? Visual angle, a small visual angle alpha, than pole 1, then it appears shorter. Like that. Then it appears. So they will ask you to explain that. Explain why poles of the same height placed in a straight line, the pole nearest you appears taller than the pole farthest. So you look at the visual angle subtended. The bigger the visual angle, the bigger the size of the object. So the one which subtends big visual angle will appear to be taller than the one which has subtended small visual angle as observed from the eye. Is that okay? Yes. Then let's go and look at, now we can look at the angular magnification. Angular what? Magnification. Angular magnification. Stroke. Magnify what? Magnifying power. Capital M. So we shall say that is the ratio of angle subtended by the final image. By the what? By the final image. Okay? At the aided eye. So aided eye is that eye which is using an instrument like a microscope. At the aided eye to the angle subtended by the object at the naked eye, at the unaided eye, unaided or naked I, i.e. magnifying power is equal to alpha prime over alpha. Then we start with microscopes. The microscopes are divided into, okay? They are divided into, there are two types of microscopes. Two types of what? Microscopes. Number one, we have what we call a simple microscope. This one has one lens. Microscope. Another one is called what? The one with two lenses that biology students normally use in the lab is called what? Compound. Compound. Make what? Then we shall start with the first one, which is simple. Microscope. Oh, another one is called magnifying glass. Magnifying what? Glass. Then we shall now explain this one. It has, consists of one convex lens. Okay? Then we say consists of one convex lens. Then we say in normal adjustment. In normal adjustment. You know, the fine image. Where is the fine image formed? The fine image is formed. The final image is formed at a near point. The final image is formed at a near point. Then we shall now say that we do the diagram. Like that. So now if it is forming fine image at a near point, then it means we have to, this is F, so this is C. Okay, like that. Then we put this one here, like that. Then we have this. So how that? Like this. This is F. The image is formed where? The image is formed here. Image is I. So I shall say the arm subtended is alpha prime. Because this is the image. So that's the arm subtended, that's the alpha prime. This is H2, this is H1. Then we shall have the I this side. Okay? Then we shall say the magnifying power. Magnifying what? Power. And it's got angle subtended by the final image to the angle subtended by the object when there is no instrument. Then for unaided eye, we say for unaided eye. So we shall have something of this nature. For unaided eye, something of this nature. Okay? Then here we shall have this. This object. The angle subtended is alpha, and the distance is d. Okay? The distance is what? Is d. This is height of object. So we say for small angles in radians. For small angles in radians, tan of alpha is approximately equal to alpha which is H not out of what? Out of D. This H1. What about for tan of alpha prime on the diagram? We say tan of alpha prime approximately equal to alpha prime, which is tan of alpha prime here. It gives us H2 divided by the distance. So this distance is D because it is formed at a near point. Okay? Distance is what? It is D. So that is H2 over D. Okay? Then we shall now say that magnifying power is equal to H2 over D times D over H1. So D will cancel. So magnifying power will now become H2 over H1. But H2 over H1 is equal to linear magnification. Is linear magnification. So linear magnification is equal to H2 over H1, which gives us remember from 1 over F equals 1 over U plus 1 over V. So this term is the same as V out of F minus 1. So therefore, capital M magnifying power will now become, this is V over F minus 1. Minus what? Minus 1. In normal adjustment. But our V is what? But our V is same as what? D. So the answer will now become D over F minus 1. However, this D is negative because it's a negative D. It's a negative D. Why? Because the image formed is what? Is virtual. The image which is formed is what? Is virtual. So they can ask us, explain why. Explain why chromatic aberration is not seen. Explain why chromatic aberration is not seen. Let me be chromatic aberration is not, does not occur in simple microscope. So they can ask you to explain why it does not what? Occur. So what we shall do, we shall just draw our diagram. Okay? We shall have our diagram. Let me say this is a lens. Then we shall have this. Then we shall have white. Let's have like this. Have this. Then here have this. Now we have this one here. Then we shall we have this that goes up to here. Then we also have this. So we have this, and then here we have in here. Now, let me say we have violet and red. This is for red, F of red, F of violet. So this is image I red, I what? I violet. So here to explain this, we shall now say, okay? We shall say, when an object O, is viewed through a converging lens, use it as magnifying glass. Various colored virtual images corresponding to say red and violet rays are formed at slightly different positions, IR and IV, along the principal axis, respectively, as shown above. These images subtend the same visual angle. These images subtend the same visual angle from the eye, subtend the same visual angle at the eye, and therefore appear superimposed, or appear to have a uniform illumination. So they appear superimposed. Thus, the virtual image seen in a simple microscope is almost free from chromatic aberration. So what I'm saying that we have a white light object, okay? Now, read this to formation of the various colors, the various components of the colors, okay, will be brought to different points along the principal axis. Read it to formation of virtual images, for example, I-red and IV at slightly different positions, okay? But now, these colors, they appear superimposed here. They appear superimposed because they subtend the same visual angle. So the issue here is that, tell us that the reason why the images are free from chromatic aberration said that when a colored object is placed in front, okay, various colors corresponding to maybe red and violet